Hello students, today we will discuss about some problems related to the transient response of simple control system. We will discuss about the proportional controller and the proportional integral controller. We have discussed the four derivations related to the servo and mechanism problem. So you are supposed to know these four derivations for proportional and proportional integral controller. Once we solve these four derivations, then these are the some important problems we will discuss to find out its transient response and how to find out the offset. So we'll discuss first about the problem 8.1, where a proportional controller is used for two first order systems whose time constant is 1 and zero point 0.5. So you can see the diagram where tau 1 is 1 and tau 2 is 0. 0.5. The value of steady state gain for controller is 5, means value of Kc is equal to 5. Consider the unity feedback control system, same that we discussed earlier. The set point of the control system is given a step change of magnitude 0.5 and you have to find out the offset for the given system. So sometimes you may get the overall transfer function, or sometimes such a block diagram will be given. From such a block diagram you have to find out the overall transfer function. So what you have to find out from this block diagram is you have to find out C of S by R of S. C is control variable, R is set point. So if you want to find out C by R, how it is to be find out is given here, is product of both transfer function Kc into 1 upon S plus 1 0.5 S plus 1. What will be the denominator? It will be 1 plus GH. So G into H is a product of all the transfer function in the block diagram. So it is 1 plus again the product of these two transfer function Kc upon S plus 1 0.5 S plus 1. So first of all you have to find out the overall transfer function of the control system in such problems, and then you have to solve it. So then you solve this accordingly. You will get this is a C by R if you put Kc is equal to 5. So 5 upon 0.5 S square plus 1.5 S plus 6 will be the C by R. Now you have to bring this equation in form of the second order system because S square is there. So you can write 5 upon 6 into this bracket. Now in the problem it is given that if the step change of magnitude 0.5 u is introduced in set point, so R of t is equal to 0.5, R of s is equal to 0.5 by s. You can introduce this 0.5 by s in the equation. C by s is equal to 0.5 by s into 5 by 6 into bracket 1 upon 0.083 s square plus 0.025 s plus 1. So you will find this equation is similar to the second order system step change. Is that right? So you can compare that equation with the following one. C of s is equal to 0.4166 1 by s into this bracket. So bracket will be 1 upon tau square s square plus twice zeta tau s plus 1. So if you compare this equation 4 and equation 5, okay, what you will get? You will get value of amplitude, you will get value of tau square, and you will get value of twice zeta tau. So tau square is equal to 0.083, twice zeta tau is equal to 0.25, and from this you can find out value of tau and zeta. Then tau value will get 0.288, zeta will get 0.434, means this value is less than 1, so this is underdamped system. So what you get? You get this is underdamped system, step change, second order system. What is your objective? You have to find out the inverse Laplace of C of S. So what will be this inverse Laplace? Will be the same that we studied in a second order system. So this will be the equation that we studied for second order step change underdamped system. So this 0.4166, this constant will remain as it is. What will be the equation? C of t is equal to this constant into, this is the equation that we studied in second order system, step change. 1 minus e raised to zeta t by tau upon square root of 1 minus zeta square sine bracket 1 minus zeta square root into t by tau minus tan inverse of square root of 1 minus zeta square upon zeta. Don't worry, this will be a big equation, but if you put value of t is equal to infinity, everything is going to become a 0. 1 minus 0 is 1. Is it right? Because there is exponential term. So C infinity becomes 0.416. You will ask why we calculated this? Because we want to calculate the offset. What is offset? R infinity minus C infinity. So you have calculated C infinity. Now what is R infinity? Will be the step change in the set point. That is 0.5, going to remain same. So offset is equal to R infinity minus C infinity is equal to 0.0834. Therefore, offset provided by this proportional controller will be 8.34. Is it right? So this is how you calculated the offset for given block diagram. Such problems are frequently asked in examination. At least one problem will be asked in examination. Now the next problem will be the problem 8.2. Again, it is a similar problem, but this is a PD controller. You will ask that we have not studied a PD controller, then how to solve? You go for solving, you will get an idea. The PD controller is used for control of first order system having a time constant of 30 seconds. So what is mean? Means this tau 1 is equal to 0.3. Is it right? So that we will discuss later, or we'll put it 30 seconds as it is. Then the value of gain of PD controller is 6. The derivative time is 4 seconds. The control system has a measuring element for which the time constant is 6 seconds. If the step of magnitude 0.16 is given to the load variable, determine the offset for system shown in the figure 2. So again a similar problem for PD controller whose transfer function is given Kc into 1 plus tau ds. This is a transfer function for first order system 1 upon tau 1 s plus 1. This is a transfer function for measuring element, that is also first order 1 upon tau 2 s plus 1. So this is a system given and you have to step change in a load variable. Means what you have to find out? You do not have to find out C by R here. Is it right? Are you getting? It will be C by U. Is it right? So you have to find out here the overall transfer function for a regulator problem. Is it right? Because it is given. So for regulator problem, C by U is equal to what? It is a product. Product of what? C by U is the, what is the block between C and U is only 1 upon tau 1 s plus 1. See here, 1 upon tau 1 s plus 1. What will be the denominator? It will be 1 plus GH, 1 plus product of all the transfer functions. So 1 plus this Kc 1 plus tau ds multiplied by first order system multiplied by measuring element. See here, see the denominator, 1 plus G into H. So see, you have to solve this C by U and you have to bring it in this form. It will come into this form. Again a second order system. So this is a second order system. C by U is equal to A upon tau square S square plus tau zeta tau S plus 1. Where what is the tau square? Compare with above equation 8. Tau square is tau 1 tau 2 upon Kc plus 1. You can find out tau. Twice zeta tau is equal to bracket, second bracket, tau 1 plus tau 2 plus Kc tau d upon Kc plus 1. That will give you the zeta value. Now you put all the values given in the problem. Tau 1 is equal to 30 seconds, tau 2 is equal to 6 seconds, tau d is equal to 4 seconds, Kc is equal to 6, and you can find out value of tau and zeta. So putting this value, tau becomes 5 seconds, zeta becomes 0.85. Again it is less than 1, system is underdamped. So what is this system now? It is underdamped system, step change, second order system. So you can write the equation like this: C by U is equal to this equation. Now we'll introduce the step change of 0.16 into a load variable. U of t is equal to 0.16, U of s is equal to 0.16 by s. So C of s is equal to this equation. So you will get this equation, C of s. You will get two different equations here. One equation where there is a s to the numerator and denominator, which will get cancelled, and there is another equation where second equation is there is constant term upon s into this. So what will be the first term? First term there will be s get cancel. Okay, it will be nothing but the impulse change. Are you getting? Second order impulse change. The second term will be step change, underdamped system, and second order, because there is a 1 upon s. So see here, again you will get this equation. 0.1368 is a remain constant. This will be the first term will be for impulse change, and the second term 0.0228 up into this term, which is for step change. Have you understood? So there is no s, so it is impulse change. You go and check impulse change in second order system, you will find the similar equation. So just you have to write this equation, because the next step, if you put t is infinity, everything becomes a 0. So C of t is become like equal to 0.228. Now here you do not have to take u infinity, because offset is not u infinity minus c infinity, it is always r infinity minus c infinity. So set point is remain constant, means r infinity is 0. So you can find out offset is 2.28%. It may be plus, it may be a minus, offset is the difference. So you can write it is 2.28%. We'll discuss the last problem. This problem is asked many times in examination because it is somewhat simpler. What is the third problem? The set point of the control system is shown in the figure. Is it right? Is given a step change of magnitude 0.1. What you have to find out? You have to find out maximum value of c and the time at which it occurs. You have to find out the offset, and the third you have to find out the period of oscillation. Draw the sketch of c of t as a function of time. So this is the system given. Again it is unity feedback system. Kc value is given 1.6. The process is given a two first order systems, 5 upon s plus 1 to s plus 1. What you have to find out here? C by R, obviously. Is it right? Because it is a step change in a set point. See where the set point is change, that will be the equation. C by R when there is R is changing, C by U when there is U is changing. So you have to understand when to use C by R and when to use C by U. So this is a servo mechanism problem. So you can write down the C by R. What will be the C by R? C by R is a product of both block diagrams, Kc into this. It is given here in the numerator. What is the denominator? 1 plus GH, 1 plus product of all the transfer functions. So it is 1 plus these terms. Understand this, then you will get this equation by solving it, by putting all the value of tau and step change. So now you can introduce RS. Okay, you can introduce a step change. Before introducing the step change, you can find out value of tau square. Tau is 0.471 and zeta is 0.354 and amplitude is 88.889. So what you get again? Zeta is less than 1. So this is underdamped system, step change second order, where this step changes occur. R of t is equal to 0.1, R of s is equal to 0.1 by s. Introduce this step change into the equation, you will get this equation. 0.0888 into 1 by s into 1 upon this whole equation. Okay, once you get c by s, can you compare this equation with second order step change? Yes. So again, you can compare this equation with second order step change. The constant remains same. What will be the inverse for c of s is c of t is equal to this constant into the equation for step change under damped second order system. What is that equation? 1 minus e raised to zeta t by tau square root of 1 minus zeta square sine into square root of 1 minus zeta square into t by tau plus tan inverse of square root of 1 minus zeta square into zeta. Is it right? So see here, you will get, putting a c infinity value, t is equal to infinity, it becomes 0.888. R infinity is equal to 0.1. What you can find out is offset. Offset is 0.0112. Offset is 1.12%. So you have find out offset now. What you have to do? You have to plot the graph. So again you can use that equation for c of t, where you have to put the different value of t and you have to find out the c of t. Are you getting? And this will be the graph for c of t versus time. So you will get this graph starting from 0.086 and it will be continue for 0.0888 and it remain constant. This is look like a step change. The last you have to find out the period of oscillation. Period of oscillation equation you know. It is a t is equal to 2 pi tau upon square root of 1 minus zeta square. You know zeta, you know tau. You can put this value, you can find out the period of oscillation is 3.164 time per cycle. So see how to find out this problem. See, then there will be so many problems. You solve these problems, okay, you will understand the process, how to find out the answer for such a block diagram where C by R is used as a servo problem and C by U which is used as a regulator mechanism problem. So you have to find out C by R or C by U. You have to find out its inverse. You have to introduce a step change and you have to find out the offset value or period of oscillation, or you can plot the graph. So these are the important problems from this subject, and thus we have finished the topics from the process control. Now remaining there are 3 chapters, out of which 2 chapters are smaller one. We can finish within one lecture. That is called as a stability method. There are 3 stability methods: Raut array, root locus, 1 lectures, and body diagram. It may require 2 or 3 more lectures. Okay, so we'll try to complete most of this syllabus before lockdown is over. So I hope you are understanding the things, and if you have any doubt, okay, we'll start discussing it. I think CR, you start one WhatsApp group for PDC, our subject differently, where we will discuss the remaining things. Thank you guys, and be safe at your home. Thank you.